continue on. That the reflection coefficient of -1 means there's going to be a 180 degrees phase shift as the wave comes back at you. And there are tutorials and videos about this out on the web, so I'm going to leave that alone. And actually, the phase shift doesn't matter for our calculation. We don't care about phase, we just care about magnitudes. Let's look at the case of, rather than free space, well, which is what it is. Well, not free space because I have that in the first one. Let's say there's an open in medium 2. There's no conductivity that can happen there whatsoever. And in that case, Z2 is going to be much, much greater than Z1 rather than our first case. For the case of Z2 being much greater than Z1, the reflection coefficient, which we remember is Z2 minus Z1 over Z1 plus Z2, is going to be about equal to 1. Okay? And what is the transmission coefficient? Notice this is positive 1 this time. Positive 1. Positive 1. For the transmission case, that expression is 2 times Z2 over Z1 plus Z2. And we can say that in this, the denominator is going to be dominated by Z1, so this simplifies to approximately 2Z2 over Z2, which is 2. Well, not approximately, it is 2. What does this mean? How can we have a transmission coefficient of 2, a reflection coefficient of 1? Isn't this some violation of the conservation of energy? Well, the answer is no, it's not. And the reason it's not is because the electromagnetic wave travels at a different velocity in this new medium, so there's a different power density than there is in the original medium. And if you look at, let's draw an analogy. I'm not even sure it's an analogy. This is kind of the way it is. If you have a resistor, I'm going to do a little bit of a segue here. If you had a resistor, okay, with some R, some resistance R, and a voltage across it, V, and some current through it, I, what is the power dissipated in that resistor? Well, the power dissipated in that resistor, power equals VI, or it equals V squared over R. In our system, let me write with a different color to call it out. In our system, V is E, electromagnetic wave. V is volts, electromagnetic wave is volts per meter. In our system, R is Z, Z naught. That's in terms of ohms. Resistance is a DC value. This characteristic impedance can have an imaginary component, but this is it. So if we had a boundary, let's say that system up from up above. So we had the incident wave, and we had over here the transmitted portion, and here we have the reflected portion. We can say, to conserve energy, E, and to use this expression, E1, EI squared over, this is Z1, this is Z2, EI squared over Z1 equals ET squared over Z2 plus ER squared over Z1. Okay? We'll pause there and just parse that out. This Z1 is this characteristic impedance. The Z2 is on this side, so that's the medium. That's the characteristic impedance of the medium through which this transmitted wave is going through. Now let's write this out with the reflection and transmission coefficients. So the same expression equals. I'm just going to deal with what's over here. So we have ET is transmission coefficient times EI, quantity squared, over Z2, plus the reflection coefficient times EI squared over Z1. Let me write this out, EI squared over Z1. We know that this is going to cancel with that, it's going to cancel with that. What we are left with is 1 over Z1 equals the transmission coefficient squared over Z2 plus the reflection coefficient squared over Z1. This is true. Let me look back at my notes here. That's the way it is, and if for this case of the, which one was that? For the open, where Z2 is much greater than Z1, and where the transmission coefficient is 2, the reflection coefficient is 1, what do we have? So we'll have 1 over Z1 equals the transmission coefficient of 2 squared over Z2 plus 1 squared over Z1. Just being very thorough, Z1 equals 4 over Z2 plus 1 over Z1. And we said that Z2 is much, much greater than Z1. So let's say Z1 is 1, Z2 is 100, or let's say it's not 100, let's say it's 1 with a bunch of zeros. So what do we have? Over on the left we have 1 equals 4 over some, let's say it was infinite. Infinity plus 1 equals, so we have 1 equals 1. So the conservation of energy holds. Okay. We got to clear my screen. We have enough background information now that we can start to draw a model of the system I intend to calculate. What we have over on the left is going to be the cell phone. It's the cell phone. And it radiates energy. And I'm going to assume it radiates it more or less in kind of a uniform direction, which is probably not true. Probably the screen which faces your head has some conductive glass in it, and so that's going to reflect most of the energy back out and away from your head. But I'm not going to assume that in this calculation. The cell phone transmits, there are two general standards for transmission. There's one that's centered at 850 megahertz and one that's centered at 1920 megahertz. And I'm going to do the calculation for this one centered at 1920 megahertz. The 1920 is an average of the uplink and downlink frequencies. This is just the middle point, but I'm going to use it because it is fine for this calculation. Okay, that energy. Oh, also there's a 2-watt peak transmission power for the cell phone. I found that somewhere on the web. I'm going to, in my calculation, assume 4 watts to include some margin of error, but that's what it is, 2 watts. Okay, first we have the air. There's some air, I'm going to assume, between the cell phone and your ear, or you can press it up against your ear and it'll be about the same. And this has, well, let me draw the whole model and then I'll write out the terms. Then we have the scalp. Then we have the skull. And finally, the brain. The brain. Air has a permeability of free space, mu naught. It has a permittivity of free space, epsilon naught. It has a conductivity of 0. We calculated earlier that its characteristic impedance is 377 ohms. And we don't need this, but for good measure, it has a characteristic, attenuation constant of 0, which we expect for a lossless dielectric. For the scalp, and I'm digging these values up from the web. I don't have the sources with me right now, but you can double check it. The permeability is mu naught. That makes sense because it's not a magnetic material. The permittivity is 46 times mu naught. The dielectric constant is 46. The conductivity is 0.7 Siemens per meter. And I calculated, when I looked at that expression for the characteristic impedance, I calculated it using the lossy dielectric, so I calculated the whole thing. And that's going to be 55 ohms at an angle of 0.07 degrees. Well, that angle just indicates a phase shift phenomena, so I'm going to, and it's very small, we don't care about phase shift, so I'm just going to call it 55 ohms. And the attenuation constant is 1 over 518 millimeters. Okay, is that large or is that small? I went through and found the thicknesses of these different layers. The scalp is approximately 2 millimeters. The skull is 7 millimeters, and the thickness of the brain, that's part of our calculation, is So you can see if you compare this 518 millimeters to that 2 millimeters, there's not going to be a lot if you ran the e to the 2 over 518. That's going to be essentially, well, this is going to be essentially 0, which means this whole quantity is going to be 1. And we're going to find that's going to be true for the skull too. Let me run through the parameters for the skull. The permeability is, again, approximately equal to mu naught. The permittivity is 8 times mu naught. The conductivity is 0.05 Siemens per meter. It's bone, but it still has some conductivity to it. The characteristic impedance is 145 at an angle of minus 0.7 degrees, which is, I'm just going to say 145 ohms. The attenuation constant is 1 over 276 millimeters. Okay, so the quantity I wanted here was 276. And again, this is going to be approximately equal to 1. So I'll note that as I do this calculation running through the scalp and the skull, I'm not going to care about the attenuation. I'm going to go on to the next video.